Okay, ready, let's go.
Okay. Dear participants, we are happy to welcome you on the third day of International Conference on Interdisciplinary Applications of Artificial Intelligence. Our program continues with the keynote speech, which will be given by Professor Dr. Tasif Izzet and Sadef Jamshid. Now, I would like to introduce you Professor Izzet and Sadef Jamshid, respectively. Professor Izzet did his bachelor's and master's in mechanical engineering from University of Engineering and Technology, Lahore, and completed his PhD from Tokyo Institute of Technology, Japan. He was awarded Endeavour Postdoctoral Research Fellowship by Australian government for his research in Monash University, Melbourne. He was awarded Commonwealth Economic Fellowship, which was held University of Cambridge, UK. He was again awarded Commonwealth Fellowship held at University College London. He is interested in lean manufacturing, Toyota production system, industrial robot modeling and development, HVAC systems, energy technology, management, planning and policy, production and operations management, modeling and simulation. He is an author a number of international research journals and has presented in conferences in Japan and UK. The co-presenter is Sadef Jamshid. She is currently a PhD scholar at Mechanical Department of University of Engineering and Technology, Lahore. Having an engineering academic background with honors throughout, she has been associated with teaching mechanical engineering students for the past 14 years. She works as an assistant professor at University of Central Punjab, Lahore. She has supervised numerous undergraduate projects and has recently won Best Innovation Award at the ICE competition at Lahore in 2019. She is also the focal person of the research group Design and Automation at University of Central Punjab, Lahore. Her current research is based on design and development of a fruit harvesting robot. Dear Professor Izzet and Sadef Jamshid, you may start your speech.
Okay, thank you very much, Dr. Alpan Ball, and thanks a lot, Professor Orhan Torkal. I'm delighted to be here, and I congratulate you on organizing this conference. I understand fully that it is a very difficult situation throughout the world. You are organizing this conference during COVID, which is really a daunting task. I congratulate you. I appreciate your efforts for academics and research and for all that. So a big congratulations from our side, University of Engineering and Technology. Thank you very much again for inviting me and my colleagues for this conference. I hope that this cooperation will extend in coming time. Okay, let's now talk. I would like to start my talk on the presentation. This talk will be divided into two parts. First, I will introduce briefly my university, what we are doing. Then we will be discussing design, development, and experimentation of fruit harvesting robot, a robot which we are trying to develop here. My student, Ms. Sadaf Zishan, is working on this project for her PhD degree. Before she starts on the technical details of design, development, and experimentation of fruit harvesting robot, I would like to briefly introduce what we are doing as a macroscopic picture. Okay, you can see this picture. This is the main gate of our university. Its name is University of Engineering and Technology. We call it UET. It was founded in 1921 in Lahore. It is the 100 years now. We have a history of 100 years. It has 5 campuses in major cities of Pakistan, around 14,000 students, including foreign and female students, and we are the biggest and oldest engineering university in Pakistan. We have different faculties and departments. The university consists of following faculties and departments. Number 1 is Faculty of Architecture and Planning department. Every faculty has different departments. This Faculty of Architecture and Planning has Department of Architecture, Department of City and Regional Planning, Department of Product and Industrial Design. Second, we have a Faculty of Chemical, Metallurgical and Polymer Engineering, which has Department of Chemical Engineering, Department of Metallurgical and Materials Engineering, Department of Polymer and Process Engineering. Then we have Faculty of Civil Engineering, which has Department of Civil Engineering, Department of Transportation Engineering and Management, Department of Architectural Engineering and Design, Institute of Environmental Engineering and Research. Then we have Faculty of Earth Sciences and Engineering, department which has Department of Petroleum and Gas Engineering, Department of Mining Engineering, and the last one in this faculty is Department of Geological Engineering. Next, we have Faculty of Electrical Engineering, which has 3 departments: Department of Electrical Engineering, Department of Computer Engineering, Department of Computer Science. Then we have our own faculty, which is the biggest faculty of the university, Faculty of Mechanical Engineering. It has 4 departments: Department of Mechanical Engineering, Department of Automotive Engineering, Department of Industrial and Manufacturing Engineering, and then Department of Mechatronics and Control Engineering. Then we have Faculty of Natural Sciences, Humanities and Islamic Studies, Department of Humanities, Social Sciences and Modern Languages, then Department of Mathematics, Department of Physics, Chemistry, Islamic Studies, and the last one is Institute of Business and Management, IBM. So this is the organization of our teaching departments. Then we have a lot of research centers. The first one is Al-Kharzmi Institute of Computer Science, then Huawei UET Joint Telecom and IT Center, then Center for Language Engineering, then ZTE UET Joint Telecom Center. Then we have Laser and Optronics Center, then Energy Research Technologies Development Center, Institute of Environmental Engineering and Research, DSP and Wireless Communication Center, Center of Excellence in Water Resources Engineering Research Center, then Software Engineering Center, then Manufacturing Technologies Development Center, Automotive Engineering Center, Nanotechnology Research Center, Innovation and Technology Development Center, Engineering Services UET Pakistan, then Center for Energy Research and Development, and the last one is Biomedical Engineering Center. So these are few research centers available inside University of Engineering and Technology. Next is we have a small video clip for you to introduce what UET is. It's a small clip. Let's have it.
close till I get up. Time is barely on our side. I don't wanna waste what's left. The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. Finding life along the way, melodies we haven't played. No, I don't want no rest. Echoing around these walls, fighting to create a song. I don't wanna miss a beat. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go.
Okay, thank you very much. This is a small clip from my university. Now I will stop my presentation here, and Ms. Sadaf Dishan will start discussing design development and experimentation of fruit harvesting robot. I stop sharing. Sadaf, please start it.
So can you please confirm you can all see my screen?
Yes, I can see you. And
Okay,
I can hear you.
Yes, we can
so
see
the
you.
topic of our research is design, development, and experimentation of fruit harvesting robot. Now, so this presentation is divided into two parts. In the first part, I'm going to tell you the importance of artificial intelligence in the agricultural sector, and then I'm going to come to the main research that we are doing. So the importance of artificial intelligence in the agricultural sector, as we all know that the population is increasing, and especially in developing countries, we have more people to feed. So productivity needs to improve. It needs to improve without compromising on the quality. So to keep the export quality consistent, we need the help of automated system, which has become a necessity more than ever now. So Pakistan is an agricultural country, and its GDP is 24% of it belongs to the agricultural sector. So hence, improved agricultural methods plays a very important role in the future economy and well-being of Pakistan. So artificial intelligence helps in increasing not only the productivity, but also helps in keeping the quality consistent. The current situation of Pakistan in agricultural sector is that currently we are lagging a lot in the fourth industrial revolution. A lot of places, majority of the places, in fact, are still using the old conventional methods in the agricultural sector. And if we do not now shift use the assistance of artificial intelligence now, we will continue to lag behind a lot in case of economy. Now, with improved technology and machines like 3D printers, smart sensors, Internet of Things, automation and control, monitoring and efficiency of work done, it is more easy and more productive now to shift to the artificial intelligence as ever before. This is going to help us to increase the output also. Now, the automation in the agriculture can be done in a lot of ranges. It can be used to improve the irrigation, as is being done, to prevent the pest control, and also to harvest crops and fruits and vegetables. So there's a large variety in the agricultural sector where artificial intelligence can be used. One of this area is obviously the fruit harvesting robots, which can help us, which has a lot of scope, not only in the agricultural countries and the developing countries, but throughout the world. A lot of fruit harvesting models have been designed over the previous years, and with increased technology and sensors, improved sensors, the models are becoming better and better, and are now moving towards more commercial application as ever before. Some of the few latest successful designs we're going to discuss that have been designed up till now, and let's discuss a few recent designs first before we move on to our research. So this is a cherry harvesting robot that was designed in 2019. And as you can see, it has a cup-shaped design with a blade, which helps the camera helps to detect the cherry tomato, and the blades help to cut the stem, and it holds the fruit. Similarly, another design that has been recently made is 5 degree of freedom robotic arm with scissors and grippers. So it is like a flower. It closes it engulfs the fruit, strawberry fruit, and then it closes. And there's a separate mechanism, scissor mechanism that has been designed to cut the branches of the strawberry. Similarly, a vacuum-based orange harvesting robot has also been recently designed, which consists of a 4 gripper finger with small pads attached to the edges to prevent damage. And it's based on a suction system so that the grip holds and it is not disrupted. Another design that has been recently drawn is again similar to the previous one, but in this it is able to avoid obstacles by pushing the irrelevant fruit and just moving directly towards the target fruit. So our research is also based on a fruit harvesting robot. Our research will focus on the automation of harvesting of one of the most top fruit in Pakistan, oranges. Oranges is one such fruit which is exported to many countries, and the oranges of Pakistan are very famous, and it's one of the top export fruit in Pakistan. So our research project aims at designing and development of a 6 degree of freedom robotic arm with a soft gripper. So we are going to not use a metallic gripper. We're going to use a soft, custom design and optimized soft gripper, which is going to help harvest oranges in the best possible manner. The prime design parameters include modeling of a 6 degree of freedom robotic arm. We're going to do the path planning, optimized gripper design for orange picking. Then we have detection of the oranges by using RGB color recognition and design control system using Arduino. For this presentation, since there are a lot of parameters, we're going to focus on the two prime areas, that is the path planning and the optimized gripper design. So the objective is to design and fabricate an orange harvesting robot to assist in quality picking of fruit best suited for export, and to validate through experimental testing in the field of efficient and quality fruit pickup by the orange harvesting robot. The problem statement, the reason why we wanted to do this project was to address the gap in our agricultural sector, the build up the gap, and to address the issue of not using a lot of technology in the agricultural sector. So we want to address this gap by using automated agricultural robot to enhance export quality of fruit harvested. And we want to prepare Pakistan for the fourth industrial revolution around the world by adopting emerging technology and to increase the food production as well as the quality. So the first thing that we did was in the path planning is to we did the kinematic analysis. The kinematic analysis is made up of two parts, the forward kinematics and the inverse kinematics. In the forward kinematics, what we do is we determine the end effector position. So the robot will determine the exact position of the end effector, and this includes three parts. First is the defining of frames. Now we define the exact number of joint angles in the frames. As you can see in the upper picture over here, we have defined the frames over here, where the red shows the x-axis, yellow shows the z-axis, and black shows the y-axis. Once the frames have been defined, we compute the Denevert-Hartenberg parameters based on the frames. Once the Denevert-Hartenberg parameters have been computed, this is for computing these parameters, the DH parameters, we have certain rules, 4 rules that we follow. And after that, we determine which axis needs to be where. So for example, one of the parameters is that the two z-axes need to be perpendicular to each other. So based on those 4 rules, we have computed the DH parameters. Once the DH parameters have been computed, the next thing that we do is we make the transformation matrix for all the 6 joints based on the rotational and displacement positions. So one by one, all the transformation matrix was made, and based on that, the end effector position was calculated. Now, once the end effector position is calculated, so we know that, for example, the end effector is supposed to reach orange number 1. So we know which position exactly the end effector is going to, the axis of we know the exact axis of the X, Y, and Z direction of the orange, and the end effector is supposed to reach that. Once the end effector position is done, the forward kinematics is completed. Next, we are going to determine the joint angles for the given end effector, and this process is known as inverse kinematics. Now, there are many methods used for inverse kinematics. The method that I have used is the algebraic method. So what we do is in the algebraic method, we use various formulas. Algebraic formulas, the cosine rule, and the projections we use for, and then based on those projections, we determine the joint angles. So we have calculated joint angles for all 6 joints: theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. This is all done based on the algebraic methods. Now, once the forward and inverse kinematic have been done, we use the software Robo Analyzer to verify if what we had calculated was correct. So, does this actually work? This kinematic analysis actually work? So, first of all, we input the DH parameters over here in the software, and we determine the forward path for the position of end effector of one part to another. Next, we also determine the workspace. Now, workspace shows all the positions where this robot can reach, the end effector of the robot can reach. So this we define the workspace. This is the whole entire workspace, which covers almost the entire area of the tree, the upper portion of the tree where the fruits, where the orange fruit is available. Next, what we did was, once the workspace had been defined, what we did was we chose one of the end effector position within the workspace. We input it over here, and then we determined what is the possible joint angle, what is the joint positions that the robot needs to take in order to reach that this particular position. So we came up with 16 possible results that for this particular one position, 16 possible joint angles are possible. So this was the inverse in kinematics, and this shows and verified this. So we also simulated the forward inverse kinematics and verified our results as well. Next, we did the dynamic analysis also. Now, there are 2 methods used to determine the velocity of the robot. One is the Newtonian method, and the other is the Jacobian method. In robotics, Jacobian method is preferred, and we also used the above method. So in this method, the basic idea is that we use the derivative of the end effector position, which is equal to the Jacobian matrix multiplied by the derivation or derivative of the partial derivative of the joint angles. So we already have the end effector position from the previous slides. We take the derivative of that. The lower position, alpha, beta, gamma, are the orientation of the end effector. So we determine the Jacobian matrix by taking the end effector position delta x, delta y, delta z, and one by one taking derivative with respect to the joint angle theta 1 till theta 6. Similarly, with delta y from theta 1 to theta 6. Similarly, for the z-axis position from delta 1 to delta 6, and we get the various speeds of the various joints. So by this method, we can determine this speed with which the robot and its joints are going to move. The next portion of the design of the research is the end gripper design. Now, the end gripper design is very, very important in this whole research. The reason for that is if you do not grip the fruit properly, it can damage the fruit, and then it is of no use. Similarly, we need the 2 main properties. We need the robot to grip the fruit properly and also without damaging it. So the 2 features that we are looking for in our gripper or end effector is that it should be stiff enough to hold or prevent the slippage of the fruit. And secondly, it should be flexible enough. It should have a good modulus of elasticity to prevent the damage to the fruit. So the steps that we did for the gripper design is, number 1, we did the compression test. So we took a number of export quality oranges, and we, first of all, we took the circumference from the center of various parts and took the dimensions. After that, we performed a compression test, and we found out that the maximum force that an orange can bear before it actually shows sign of damage is 80 Newton. And also we, from this, what we found out was that from the circumference, we found out that the gripper design should be such that it should be almost half of the circumference of the orange. So our gripper should be designed keeping that in mind. Mold design, now we are using a soft gripper design in the research. The reason for using a soft gripper is because we do not want to use metallic gripper, is because that can damage the fruit and the quality of food. We do not want that. Since fruit is a delicate object, we want to design a gripper which is although flexible and stiff, and we need looking for a material which is stiff, which is flexible, yet it is of a good quality and not applying excessive pressure. So the material that we shortlisted was EcoFlex 20. This is a silicon material which is very flexible. You can see the properties of EcoFlex here. It is very flexible. It has a very good Young's modulus of elasticity of 170 kilopascals. It has a very good strength also of 160 psi. And you can see it has a good hardness, and the elongation elasticity is also very good. It's 845%. So we decided to use this material to design our soft gripper for the holding of and gripping of the orange fruit. So the first step was to design the mold on Creo software. Creo is a CAD software where we designed the dimensions, keeping our orange in mind. So the finger length was 13 centimeter, and this was again chosen keeping half of the circumference of orange in mind, so that it holds the orange properly, just like our fingers. The width was kept was 4.5 centimeters and thickness is 3 centimeters. The mold should have more than 7 grooves. The reason is so that should have more than 3 grooves. We kept 7 grooves. The reason for keeping 3 grooves, more than 3 grooves, is because if you have less than 3 grooves, it will not bend. The gripper will not bend and not hold the fruit as we want. So we have chosen 7 grooves for it to bend in a proper manner and show a proper curve position to hold the fruit properly. Okay, so EcoFlex comes with 2 mixing of boxes, A and B, and we can mix A and B accordingly to adjust the hardness and the flexibility as we desired. We use the ratio 1:1 of both A and B mixture, and once the mold was made, we poured the mixture over here and let it cure for 4 hours minimum. We let it cure for at least 1 day. We left it for a longer time for it to cure. Now, also the structure analysis of the soft gripper was done. Now, since all the 4 fingers for the gripper design is uniform and same, so if we do the structure analysis on 1 finger, it can be assumed that it behaves similarly for the others as well. So we did the structural design only for 1 finger on the ANSYS Fluent software. Now we chose a static pressure, and we did after applying various. We imported the model from CAD software, again designed on Creo, and we imported it in ANSYS Fluent. And over here we applied, we did the structural analysis by applying static pressure. Now again, keeping the same criteria in mind, we applied the pressure 1 by 1, and we saw how it will behave under pressure. So we can see that as the pressure is increasing and the force is increasing, the bending is increasing. So this shows us the relation of the force versus the bending angle of the gripper. So we calculated the bending angle for various pressures, and we found out that for our maximum pressure, the deformation needs to be 42 degrees. So our gripper fingers need to bend at an angle of 42 degrees each in order for our fruit to be held properly. So we also did the stress and bending moment calculation of the gripper, and we found out that the maximum stress that it can bear is 1.89 megapascals, which is again a very good value, keeping EcoFlex in mind. Next, we purchased a compressor with a gauge in it. The reason for purchasing this was we want to, when we apply pressure to the gripper, we want to see how much pressure is being applied. So the gauge is going to help us monitor and see and control the amount of pressure that we need to apply. And we should know where to stop, and it's not just simply, it's not a random applying of pressure. The gauge is going to help us control and monitor what pressure is being applied. So this is basically the equipment that is going to be used for the testing. The next thing that is left for this step is the testing. And in the final testing that we're going to do with the end gripper is that what we expect is that at an angle of 42 degrees, when we apply a force of 80 newtons, converted that to pressure, it should be able to hold the fruit without damage properly with a firm grip. And we are hoping that the analysis done on ANSYS Fluent will be similar to the tested results. Thank you. So if somebody has any questions or you have a comment, you're most welcome to ask.
Thank you for your speech, Professor Izzet and Sedef Jamshid. It was a very interesting talk showing the state-of-the-art technology application in agricultural sector. And I want to say that I really enjoyed the video you shared. I wish to walk there and see your campus with my eyes. We appreciate your collaboration, Professor Izzet and Sedef Jamshid.
Thank you so much.
Thank you so much. Thanks a lot, Professor Dr. Alpan Bal. We'll be in touch, inshallah.
Inshallah. Thank you.
Thank you very much.
Well, on behalf of our organization team, I greet our speakers and valuable participants with respect. Our program will continue with the panel of artificial intelligence applications in production and service systems. You can access the Zoom links provided in our website and Telegram channel. Wish to see you on our panel.